Today we're jumping into a paper that really makes you rethink some core assumptions in generative AI. It's called What Matters for Representation Alignment: Global Information or Spatial Structure by Singh and colleagues. And the big idea here, for years, has been pretty simple. For representation alignment, or REPA, you'd pick a strong pre-trained vision encoder. And the thinking was, the better that model is at understanding the world, global semantics, measured by ImageNet accuracy, the better your diffusion model will be. But here's the surprise finding, and it is a big one. This paper shows that that's just not true. They tested 27 different encoders and found that generation quality isn't driven by that global knowledge. It's driven by the model's spatial structure, the correlation between ImageNet accuracy and generation quality. Super weak, like 0.26. But the correlation with spatial structure, it's incredibly strong, over 0.85. And the fix they propose, iREPA, is so elegant. Just two simple changes to the code, a convolutional projection and a spatial normalization layer that'll focus on transferring those spatial features. And it just works, consistently boosting convergence speed everywhere they tested it.
So, to set the stage, let's just quickly talk about what REPA is. Fundamentally, it's a distillation process.
Right.
You're taking a really powerful pre-trained encoder, something like a Dino or a CLA, and you're using its knowledge to guide the training of your diffusion model. You force the features inside your new model to match the features of that big teacher model.
And that's a huge deal because it speeds up training dramatically. You get much better images, much faster.
Exactly. It's a massive accelerator.
And the story we all told ourselves was that the key ingredient was semantic understanding. There are quotes in the literature saying things like, when a diffusion transformer is aligned with more semantically meaningful representations, it exhibits enhanced generation performance.
Right, that was the global semantic assumption. And our best proxy for that has always been ImageNet 1K accuracy.
But finding one in this paper just pulls the rug out from under that idea. They show higher classification accuracy. It doesn't mean you get a better teacher for generation.
It really doesn't. In fact, sometimes it's the opposite.
Okay, so let's get into the specifics. What were the counterexamples that made them realize something was wrong? I know they compared two models, PE Core G and PE Spatial B.
Yes, and this is where the story completely flips. PE Core G is, on paper, the champion. It gets an 82.8% accuracy on ImageNet. PE Spatial B is way behind at just 53.1%.
So based on all conventional wisdom, you'd bet on the 82% model every single time, no question.
Of course. But when they actually used them for REPA to train a generator, how did the quality stack up? And we're measuring this with GFID, where lower is better.
Where are the scores?
The powerhouse, PE Core G, ended up with a GFID of 32.3. So worse generation quality. The so-called weaker model, PE Spatial B, it got a GFID of 21.0.
Wow, that is a massive difference. Going from 32 down to 21 is,
yeah.
That's not a small tweak. That's the difference between a pretty mediocre image and something that looks good.
It's a night and day difference. And it wasn't a one-off. They saw the same pattern with other models. WebSSL1B, which has a solid 76% accuracy, also did worse than the spatially tuned model.
But the craziest example had to be the SAM2 encoder, right?
Oh, absolutely. The SAM2S model is tiny. It was built for segmentation, not classification. It gets an abysmal 24.1% on ImageNet.
24%. So it can barely tell a cat from a car.
Pretty much. And yet, when they used that as a teacher for REPA, it produced better images, a lower GFID than encoders that had classification scores 60% higher.
That's just wild. It's clear proof that the thing that makes a model good at classification is not the same thing that makes it a good teacher for generation.
It's a totally different skill set. And they proved this with a really clever, controlled experiment. They decided to deliberately inject more global information and see what happened.
How did they do that?
They took the CLS token, which is the transformer special token for summarizing the whole image, the global information, and they mixed it back into all the local patch token.
And just as you'd expect, the classification score went up. It jumped from about 70% to almost 79%. The model got better at ImageNet.
It did, but the generation quality.
It got worse.
It got significantly worse. The GFID went from 19.2 up to 25.4. This is the smoking gun. Actively improving the global semantic signal hurts the generation performance.
So it's like the global information is actively interfering with the spatial signal that the diffusion model actually needs.
That's exactly it. It's adding noise. Diffusion models are fundamentally geometric. They need to learn where to put pixels. ImageNet rewards models that are great at throwing away all that where information to just figure out the what. It's the opposite of what you need.
That brings us perfectly to their main hypothesis then. If it's not global info, it'd have to be spatial structure. So how do you even measure something as abstract as spatial structure inside a neural network?
That's finding two. And the way they quantify it is by looking at spatial self-similarity. A vision transformer chops an image up into a grid of patches, right?
Right, the patch tokens.
They just measure the cosine similarity between all of those patch tokens. A representation has strong spatial structure if patches that are close together in the image are also very similar in the feature space, and patches that are far apart are very different.
Okay, and they came up with a specific metric for this, LDS, which stands for local versus distant similarity.
Exactly. LDS just formalizes that idea. It calculates the average similarity of all the nearby patches and subtracts the average similarity of all the faraway patches.
So a high LDS score means you have sharp contrast. It means the feature for a patch of grass is very similar to the patch of grass next to it, but very different from a patch of sky on the other side of the image.
Precisely. It gives the diffusion model clear boundaries. It tells it where one thing ends and another begins.
And this is where they ran the big analysis across all 27 encoders.
Yes, and the results are just undeniable. The correlation between linear probing accuracy, the global metric, and the final GFID was basically zero, a value of about 0.26. It's just noise.
But the correlation between their spatial metric, LDS, and GFID?
It was over 0.85. An incredibly strong negative correlation. The higher the spatial structure score, the lower and better the GFID.
That is a causal link. There's no ambiguity there.
None. And it holds up across different metrics they design, and it holds up when you scale the diffusion model itself from a small one to a really large one. The spatial correlation stays strong, while the classification one stays weak.
It's such a robust finding.
Yeah.
And it even explains why, some classic computer vision features like SIFT or HOG can actually give you a decent boost with REPA.
Because they are purely spatial. SIFT and HOG are all about local gradients and structure. They have no concept of a cat. They only know about edges and corners. And it turns out that's what matters most.
So this spatial insight explains all those weird results from the beginning. PE Spatial B won because it had a better LDS score. And adding the CLS token hurt, because it smeared that global info everywhere, which killed the spatial contrast.
Exactly. It connects all the dots.
Okay, so if spatial structure is the engine here, that brings us to finding 3. How do you actually optimize the process to transfer more of it? This is where they introduce their fix, iREPA.
And iREPA is just so elegant because it's two very simple, very targeted changes. We're talking less than 4 lines of code in total.
All right, what's the first modification? It has to do with the projection layer, right?
It does.
Yeah.
Standard REPA uses a simple 3-layer MLP to map the dimensions from the diffusion model's features to the encoder's features. But an MLP is global. It treats every feature the same, regardless of its position.
Which, as we just established, is a bad thing. It's a bottleneck for spatial information.
It's a bottleneck. It's lossy in a way that smooths out the very contrast you want to preserve. So the fix is simple. They replace the MLP with a lightweight convolutional layer, just a 3x3 kernel.
Because a convolution is inherently local. It has a spatial inductive bias built right in.
That's it. It's designed to preserve local relationships, so it's a much better translator for spatial information.
Okay, that makes perfect sense. And the second change deals with the target features themselves.
Right. Even in a good spatial representation, all the patch tokens still share some global average component. It's like having too much ambient light in a room. It washes out the contrast and makes it hard to see the sharp edges of objects.
So you need to turn down that ambient light.
Exactly. So the second fix is a spatial normalization layer. They just normalize the patch tokens from the teacher encoder across the spatial dimension. They compute the mean and variance across all the patches and subtract the mean.
So you're deliberately throwing away the global information, the average of all the patches, to make the differences between the patches stand out more.
You're sacrificing the global signal to amplify the spatial contrast. And the ablation studies show both changes are critical. The convolution preserves the signal, and the normalization sharpens it. Together, they create iREPA.
So let's talk about the practical results. How much better is this? Is it just a small gain, or does it really change the game?
It's a huge gain in practice. iREPA consistently leads to faster convergence. That means you reach your target image quality, your target GFID, in far fewer training steps. And this was true across all 27 of the encoders they tested.
What about for people training really large models? Does the benefit fade as you scale up to, say, a SciTXL?
It's actually the opposite, which is fantastic news. The percentage improvement actually gets bigger with larger models, so these spatial fixes are even more impactful when you're training the biggest, most expensive models out there.
And it generalizes. It's not just for this one specific REPA setup.
It generalizes everywhere. They applied the IREPA modifications to other methods like REPE and mean flow and saw the same consistent gains. It works with or without classifier-free guidance.
What about outside of latent diffusion? They tested it on pixel space models too, didn't they?
They did, which is a big deal because those can be slow to train. They combined IREPA with the GT framework and showed it accelerated convergence there too, enough to outperform other state-of-the-art pixel space models.
So the principal prioritized spatial structure isn't just a quirk of diffusion transformers. It's a fundamental aspect of image generation.
It seems to be. The benefits even held up when they moved to higher resolution images and to multimodal text-to-image tasks. The core insight is just incredibly robust.
So if we just, synthesize all of this, the big shift for anyone in this field is that we need to stop using ImageNet accuracy as a proxy for a good generative teacher. We need to stop prioritizing classification skill and start prioritizing geometric fidelity.
That's the key takeaway. This paper gives us a clear reason to revisit how we even choose our foundation models for these tasks. The best classifier does not make the best teacher for generation. We need to look for, or maybe even build, encoders that are explicitly good at maintaining spatial coherence.
And it opens up the door to reconsidering older models or even classical methods like SIFT that we might have dismissed, because we now understand that their strong spatial signal is exactly what REPA needs to succeed.
And that leads to a really interesting final thought for you to chew on. If maximizing the spatial structure is the key to faster and better diffusion training, what does that mean for the next generation of self-supervised models?
Right.
Maybe we shouldn't just be training them to be good classifiers. Maybe we should be explicitly designing their pre-training tasks to make them the best possible spatial teachers for generative models. That change in objective could be the next big leap forward.